So we'll go over a dynamic pricing example, which is going to use dynamic programming, which we talked about last time. And this is sometimes referred to as the airplane example, but you'll start to realize this example could be used in other cases too. So in this example, we have an airplane, and we have the same seats but different prices. So there might be business travelers, those would be people willing to pay a lot more money than vacationers, and then maybe frequent flyers. The cost to the airlines is pretty close to zero, and other different levels of flyers, all sharing the same seat. So the seats have the same values, but we might be able to figure out a way to get more money out of some people than others. So we're going to use a convention that says level 1 is the lowest fare, and then level 2 is the next lowest, and we can work our way up to many levels. So let's say, for example, we could have vacationers. So vacationers might be people who can plan their trip weeks, maybe even months in advance, and typically they stay over at least one Saturday night. Business travelers tend to be people who will pay much more money for airfare because their plans are made kind of suddenly. You know, they're on the phone talking to somebody, they're about to close a deal, and then they say, oh, why don't you, come, why don't we meet in person? So, and then business travelers also, their company pays for their hotel bill, and so they don't want them staying like a whole week. It might just be to go to a 2-hour meeting. So they're not likely to stay over Saturday night. So that's why you see a lot of airlines, they'll give you a cheaper fare if you're willing to stay over Saturday night. They assume you're a vacationer rather than a business person. Okay, so that's just like a little bit of a background. Okay, so now we're going to make an assumption that level 1, which we said is our lowest fares, we're going to allow so many seats on our airplane to be sold at level 1. So as we're selling those, we're not selling level 2s also, because, well, why would somebody buy it if they could buy it at the level 1 price? Then once we switch to level 2, you can't go back and buy level 1 pricing. So as we go up the levels, we're getting closer and closer to when the plane is going to depart. So we might see something like, if you book 7 days in advance, you get a lower price, and then 7 days or less, you pay the next level price. And I just wanted to keep it simple. In our example now, we'll just have 2 levels. But if you think about it, we can just extend this to 3 and 4 and 5 levels too. So let's say for our example, we have an airplane that has 100 seats. And let's say vacationers pay $59 each way. Business travelers pay $99 each way. So these will obviously be short flights, because airfares are a lot higher now than that. And let's say the vacationer price stays in effect up until 7 days before the flight, and then within 7 days to go, the price switches to $99. And then once the flight takes off, there's no more selling tickets. So we could send the plane out with empty seats. Okay, so the question is, it's popular in the airline business to use the word protect. So we'd say, how many seats would we protect for business travelers to maximize the amount of money we get out of the flight? So maybe out of the 100 seats, we might say, well, we're going to protect 50. So what that means is we'll sell up to 50 for people who want to book more than 7 days in advance. And once we hit the limit of 50, we stop selling to them. And then we can switch to the higher price. So the goal of our examples is going to be to find that protection level, is typically what they call it. Okay, so we could have a situation where we protect too many seats. Let's say, for example, suppose we reserve 70 seats for business travelers, and then 100 vacationers show up and want seats. Well, we would sell 30 seats to them, and then let's say after that, within 7 days before the flight, we only have 40 business travelers show up. Well, we would sell all 40 seats, and then we're going to end up having 30 empty seats as the plane goes out. So it would be kind of like wishing we could. We wish we knew in advance it was going to be only 40. We reserved 70, kind of hoping 70 would show up, and only 40 showed up. So if we had known that, maybe we could have sold more seats to the vacationers and gotten more sales. So that's an example where we protected too many. We could also have the example where we're protecting too few. So suppose we reserved 30 seats for business travelers. 100 vacationers show up, so we sell 70 of the seats, and then we stop. And then suppose, again, the 40 business travelers show up. Well, we only have 30 seats left.
Correct.
So we're selling 30 when we could have sold 40 at the higher price. So therefore, in hindsight, we realized we sold too many seats at the lower fare. So what would ideally, in a two-level system, what would be the ideal piece of information to know? If we knew. So
How many to protect?
yeah, well, if we knew exactly how many people were showing up, we know exactly how many to protect, right?
Yeah.
Okay, so example 1.1. This is, the airplane has 100 seats. Fare 1 is $59, fare 2 is $99, just like before. And we know that exactly 40 people are gonna come and pay $99 within the last week. So how many would we protect? And let's say also, there's an unlimited number of people who come and take the vacationing seats. So then the question is, how many should we protect for class 2? Well, if we know it's exactly 40, we would protect exactly 40. If we protected less than 40, then we're gonna be selling seats to people for less airfare. And if we protect more than 40, we're gonna have empty seats. Because all the $59 people come 7 days before the flight, and then we only sell the 99s and we don't get enough people. Okay, so in that case, we kind of had a crystal ball. We can look into the future and see exactly 40 people were coming. So let's say we don't know how many people are coming, which is more the real world. Suppose hypothetically, we had 50% of, let's say for some reason, we knew this piece of information, that there's a 50% chance 40 people will come in the last week, and there's a 50% chance that 60 people will come. But we don't know which one. So what would be a real world example like this? Maybe this is some town where there's a, I don't know, a sports event, and if the team wins, they go to the next round of the playoffs, and that'll bring in a lot more people, but there's a 50% chance they'll win and a 50% chance they'll lose. So if this was the case, then how many seats would you protect? If there's a 50% chance, it would be 40 people. 40 people will want the high price, will pay the high price. And a 50% chance that 60 will. Like off the top of your head, what do you think you might protect?
You would protect 60 maybe, because that's a bigger number. And it's the probability is the same, 50% and 50%.
Okay. Let's see, does that come out right here? Let's see. Well, if 40% of the people come, we could get 59 times 60 plus 99 times 40. That would be if we protected 40 seats.
Yeah. If you protect 60.
Oh wait, no matter how many come, we know at least 40 are going to come. It might be 40, it might be 60. So you were saying we should protect 60, the higher number. Okay, so if we protect 40, we will definitely get 99 times 40 and 59 times 60. That will definitely get. If we protect 60, we will get we will get 40 times 59.
And 99 times 60, is that?
Or 40.
Or 40, okay.
Right, because we don't know, is 40 people gonna come or 60?
Yeah.
So we would end up doing a computation like saying, we would compare, well right now we're thinking there's two choices. We should either protect 40 or 60. So those are, well, would it make sense to protect less than 40?
No.
No, because that would only make things worse, right? Less than 40 would mean we're selling seats for $59. We know for sure we could get 99 for, right? So that would never make sense to go less than 40. And would it ever make sense to go more than 60? No, because those are guaranteed empty seats. Right. So our answer could be 40 or 60, and possibly even between 40 and 60. But okay, so if we looked at the two extremes, if we protect 40 seats, we will sell 60 at 59 and 40 at 99 for sure, because we're definitely gonna get 40 people to show up.
Correct.
If we protect 60, we'll sell 40 at 59 plus either 40 or 60.
Or something in between.
Well, that'll be the next
That's the
example.
next-
But
okay.
right now, this is, for some reason, it's either exactly 40 or exactly
Yeah,
60.
because it's equal probability, you're saying it's 50% and 50%, so.
Right.
Okay,
So then it would end up being, there's a 50% chance we will get, if we could probably do that on an Excel spreadsheet, we could say, 40 times 59 plus 40 times 99, that's one way, and then 40 times 59 plus 60 times 99, that's another way, then take the average of the two. And if we care about expected values, we would just take, the average of the two and compare that to the other answer. But there also, is it possible it could be the best answer somewhere between 40 and 60? I think in this case, I didn't solve this one, but I think it's linear. I think it would go, I think that we would take the two answers. I think it ends up being that it would be better to protect 40 because 60 times 59 and 40 times 99 will be higher than the average of the other two. And I think those two numbers would just have a linear line going between the two if we pick numbers between 40 and 60. So for example, if we protected 50 seats, then we would get 50 times 59 and either 40
or 50.
or 50, right, and that's an important concept. So it goes up to the amount you protect or the amount that showed up.
Yeah.
So we don't know how many are gonna show up, but we know we're maxed out by the amount of seats we have available to them. So I think in this case it would be a linear number between the two. So in this case, I think we'd want to do, we could kind of do for a homework, we could just figure out what's the better one. But I think it would be better to protect 40 seats and let 60 go out at $59. And I think if this price was more than half, less than half of this, if this was like $39, then it would be better to take your chances and hope the higher ones would come. If this is half of this, then I think it doesn't matter. Either answer would come out the same. Okay, so now this isn't kind of realistic to say like there's a 50% chance there'll be 40 people at the higher fare and a 50% chance it'll be 60. It would be kind of all the numbers, pretty much all the numbers 1 to 100 would have like some kind of, every number would have its own probability, right? So do you happen to remember like what would be, so for example, a uniform distribution, that would be like 0 to 100, each one having an equal chance. That's one way we could model it. But is there any, do you remember a distribution that is kind of geared towards a model something natural in life like this? Like, so for example, if you said, I'm gonna roll a dice over and over and over until I finally get a 6. So the expected number of rolls would be 6 until you get the first 6. Could be one, it could happen on the first roll, it could happen on the second. It's expected to be 6, but it could be 7 or 8 or 9. And it could actually go off into like very high numbers. That has a very low probability, but it could go off into very high numbers. But there's a probability distribution that covers that, and that's kind of the case we're in here. That there would be an expected number. We could look at flights in the past and say, well, it seems like we get an average of 40. We get an average of 40, but sometimes it could be 80 or 90, sometimes it could be 20, but it kind of averages 40. But it's not like uniformly distributed, because that would be like, that would only go 1 to 80 and then have to stop to do it uniformly. And if we did it normally distributed, which is like a bell curve, it has to start at 0, can't be a negative number. So if it's a bell curve around 40, and it went as low as 0, then it would kind of have to go as high as 80 and stop again. But do you remember a distribution that kind of like goes up a little and then hits its mean, and then kind of tails away off to infinity. I don't know if that one, if that rings a bell, but from your probability class. But there's a distribution called the Poisson distribution,
Okay.
and it models exactly this case. So, so let me just tilt this. So basically, Poisson distribution is, have you ever seen this word Poisson before?
Yeah, yeah, I've come across it, but I just can't remember exactly, what it
Okay,
is.
no, but I mean the word itself, it's a French word. Have you ever
Uh-huh.
seen it, like, you ever see it on a menu? It means,
What, no,
it means fish in French.
oh, wow.
So the distribution it kind of has like, it hits the mean, and then it kind of like tails away off to infinity. And depending on whatever you set as the mean, that's the lambda.
That's the highest point,
Yeah, that's the highest point, that's the most likely one to happen.
correct.
And so, like, for example, when lambda's 4, that's this set of purple ones here. So kind of, it's a very natural, like, questions like how often on a roulette wheel does your favorite number come in? So if your number only comes in 1 out of every 38 times, it would be a curve like this, it would go up to around 38 and then it would taper off to infinity.
Okay.
But that's like kind of very natural for something that kind of starts at 0, has an average, but could go off to infinity. So I always say, there's a famous French mathematician named Poisson, but it just so happens it means fish. So I say, like, the curve kind of looks like the top of a fish. But that's not really why it's called Poisson. Okay, so what we could do is we could take the parameter, whatever the average is, and we can punch that number in and then figure out what is the probability of all the numbers up to that point. And that follows pretty much, maybe a real world example would be modeled pretty close to the Poisson distribution. So, this might be a little bit more realistic. Let's say we had 2 fares, $59 and $99, 100 seats on the plane. And we said the number of people wanting to pay the fare 2, and let's say we observed this from the past. We noticed that it comes on average about 40, and it's somewhat distributed like a Poisson distribution with the parameter 40, meaning the average is 40. And again, there's an unlimited number of people who will pay fare 1. Well, now right off the bat, this is a little unrealistic, because if we were running in airlines and there was an unlimited number of people who pay fare 1, we'd raise fare 1, right?
Correct.
Because there's just tons of it. It's obviously too low because everyone keeps showing up. So the question then becomes, in this case, how many would we protect? So how do we do this? If we were to take the last example, where there was a 50% chance that it would be 40 and a 50% chance it would be 60, we calculated it at both points and took an average.
Correct.
And then said, let's compare that average and then, find what's the best number out of all the protection levels, what's the best protection level for that probability. Now we have tons of points, because really, it's possible nobody shows up and wants to pay. It's possible 1, possible 2, well, actually all the way up to infinity, theoretically. But we would have an average of about 40. So it'd be nice if we calculated for each one of those, if we picked a protection level, and then for each one, we decided to, let's see. So, sorry. For each one, we decided to just take many samples. Okay, so this is some Matlab code that'll run that simulation for us. Let me just zero in on this. Okay, so what this code's going to do is so what this code is doing is we're saying, okay, so clear all is take all the variables we've set, clear them, make them all go to the default values. So the capacity is 100, and I'm just starting off with a guess of like a protection level of 55. I'm creating a variable called lambda 2, so this is the lambda for level 2. we could actually, the reason I wanna do that is, maybe later on, we'll say, well, the vacationers come at a rate of like, Lambda 1 is maybe 100. Like maybe 100 people show up, but sometimes it's 80, sometimes it's 120, but we'll get rid of the idea of they all, unlimited numbers of people come. So then price 1 is $59, price 2 is $99. We're gonna run an experiment 10,000 times.
Okay.
So we're gonna let the variable I go for the values of 1 all the way up to 10,000. And now what we're gonna do is I'm gonna make an array called demand 2. So that's the number of people showing up demanding those seats. And Matlab has a Poisson random variable. So it's Poissrnd is a function. You give it a number, say the average is 40, and it spits a number back to you. So it might come back, it might say 38, it might say 52, but it averages 40 and it follows the Poisson process. The demand for level 1, which is the $59 fare, that is going to equal what? Well, it's going to be 100, the number of people on the plane, minus however many demanded the level before us. That's going to be the number of leftover seats. That's the highest number, or the demand will be 0. So there's a function called maximum. You could give it 2 numbers, and Matlab will figure out what the 2 numbers are and then tell you what the maximum is. So for example, if the Poisson distribution with a lambda of 40 returned 35, it just said 35 people showed up this time. The demand here would be 35, and then 100 minus 35 would be 65 or 0, whichever is larger, which would be 65. So it would be like to us, 65 people came up, vacationers came up to us. Then we have another vector, so vector, these are all indexed by I, vector called revenue. So it's price 2, which is $99. So I'm just doing that, I'm calling variables so we can just kind of change these numbers and run the experiment again with different prices later on.
Correct.
Because these might not be the greatest prices. We might want to say, hey, let's make this $69. Now making this $69 will make the number of people show up would be a little bit less, but we'll have to take that into account. So, so price 2 times the minimum of demand 2 or the capacity of the plane minus the level we protected. So let's say we protected 55 seats for the business class people. So if 40 show up, then what that means is we want the minimum out of either the 40 that showed up or 100 minus 55, the 45 that we reserved for them.
Okay.
So that tells us how many showed up. And if more show up than we reserve seats for, then unfortunately we can't sell them all. So we're taking the minimum of how many seats we allowed for them and how many people showed up. And then whatever's the smaller of the two, that's what we can sell. So we sell that times price 2, and then plus price 1 times the amount we protected. And this is, we don't have any probability distribution here because we say in this example, we have unlimited numbers of people showing up. And then so we created this vector. So we have 3 vectors. We have demand 2, which is filled in by Matlab. That's all the random numbers with the Poisson distribution. Then the remaining seats are filled in by, we kind of figured that out, how many seats are left over for the vacationers. Then the revenue is, so now we have, it's like we have 10,000 airplanes going out.
Correct.
And we're running the experiment 10,000 times. So we can figure out the revenue. We have a vector of 10,000 revenues for our 10,000 airplanes. And then Matlab lets us do what is the mean of a vector. It'll just add up all the numbers and take the mean. And if you say a variable, and it'll print out the result. So we can run this. So we can click there. And it took a little while. So let me just see if I think that's, yep. Okay, so this says 7, all right, this is 7.1266 times 10 to the 3. So $7,126 is what we got from that airplane. Now, what do you think would be the best level to protect if on average 40 people from the higher paying fare will show up on average, but it could be all different numbers, but it averages 40. What would you think would be a good protection level? Would it be 40? If we did,
Maybe more than 40?
Yeah,
If
because-
the average is 40, so you know for sure that 40 people show up in the business class? Is
well, no, they average 40. It could be 35,
okay.
could be 50,
that- Okay,
but it kind of averages 40. So if we protect 40
40.
seats, then we're going, so, to have the plane go out with empty seats, that would mean it would come back with a number less than 40. But it's a Poisson distribution, so if it's less than 40, it tends to be close to 40. And if it's greater than 40, that kind of goes off to infinity. And there we're filling in those numbers with the lower fare people. So let's just try it. Let's see if we get. Oh, yeah, so that was $6,300.
mhm.
And that's on 10,000 runs of the airplane. So if we made it, what if we made it an unusually high number? Like 60. Intuition might not let that. This is 7,200 with 60, $7,100 with 55, and 6,300 with 40. So it's not intuitive, right? It's all, because this looks like, see, if we make the protection level 60, on average 40, so what that means is we sell 40 seats to the vacationers,
Good.
and then save the remainder for the business class, but on average, we're gonna let 20 seats go out empty. Now, we might get 60 to show up, which would be great. We might get 10, which would be really bad, but this is a running average of them all. And it's not intuitive, but it ends up being a higher number. So then, what I wanted to do, let me see if this works. I added, this is basically the same code. This is pretty much the same code. This part in the middle was on the last one, but now I put another loop where I'm making the protection levels go from
Oh, okay.
55 to 70. So instead of, like I used to say, the first example I had, I said protect one equals 55. Now I'm kind of ignoring that. I'm now saying let it go from 55 to 70. So now we're going to get the experiment running with a bunch of results. And I just want to see how well these do. So with protection levels of 55, it's going 7,100, 7,200, 7,400, 7,250, 60, 40, 32, 72, 7,100.
Going down.
Yeah, so it was, where's the best answer? It was 7.25, 7.25, 7.26, 7.24, 7.23. So now again, we're doing simulation, so these answers aren't perfect, but it looks like it's somewhere around
7.26.
this one.
For 61, yeah.
Yeah, so for letting 61 seats be reserved for the business class, we get the best expected value out of the plane. And that would mean, because the expected value of the Poisson distribution, because it's expected to be 40, so that means, you know, it could be 30, could be 80, but it's expected to be 40, we can expect to let 21 seats go empty.
Correct.
And even that's still the best
Yes,
answer.
option.
And then that's where, and airlines do all this stuff. They kind of model it very, very close to a Poisson distribution, and it's kind of based on the past. What we could do later on is we could add to this by saying, and like we could have 4 levels of classes. So what are some common ones? There's the business class, like within 7 days.
And then there's the first class, which is a
Yeah.
very few seats.
Right, so that's another one they do, where they'll take out 3 seats and put in 2 big seats and sell them
Yeah.
for, they'd have to sell them for at least 1.5 times the price just to
Wow,
break
yeah.
even, but they end up selling it 2 or 3 times.
Yeah.
And then also frequent flyer miles, you could make like the lowest level, you could like for an airline, you could reserve maybe 10 seats for frequent flyers. And what that ends up doing is, they're trying to get the ones that will go unsold, because it looks like the best protection level to pick leaves very often unsold seats.
Mhm.
So they could maybe let some of those go for frequent flyers. And then the other thing they could do is they could overbook the flight, because they're kind of anticipating that the way they're doing it is they're gonna have some empty seats. On average have empty seats, but not always. And then they can overbook the flight, and if they overbook the flight, they pay maybe a bigger penalty, because they have to like give people an extra free flight and pay for their hotel to keep them another day. But maybe they could sell some extra seats, and if people do not show up for the flight, then they're just
Yeah.
filling up empty seats. So there's, I mean, so basically the levels, to add more levels to this would not be too much harder, right? If we wanted to have a 3rd level, we would just, the function that says how many people are gonna be at level 1, when there's a 2-level system, it's gonna be the whole plane minus everyone from the level 1 above us. Now we'd end up having everyone from the level above us, or 2 above us, or 3 above us. We'd have to add them all up to get the demand for every lower level, so it would be kind of done doing a dynamic programming thing. But it wouldn't be that much harder. It would just be, you know, adding more levels and then running the experiment enough times. We might even want to consider running the experiment more times once we have more levels, because if the distribution of the highest price, if the random variable of the highest price one comes out unusually low, it makes the next level have a lot more freedom to buy more of a protection level, have a higher protection level.
So more simulations would give us a better
Yeah,
pricing in terms of the maximum revenue.
yeah. So yeah, so it might be, because right now the only randomness is this one random variable. Every flight we say, we have to guess. Well, basically what we're doing is we're saying, how many seats should we sell to the vacationers in anticipation of how many business people are coming? And the business people is a random number we don't know. So we're trying to guess the best number for a number we don't know. Now, if we had 3 levels, we have to say, well, how many people are going to buy, let's say, in the last week, and maybe we have a 2nd level that was the week before the last week, and we don't know how many are going to come from that class. So now we have 2 random variables that we're trying to predict the vacationers for. Then the other thing is we might start to notice that those different classes are somewhat correlated. So for example, if we had, let's say just as an example, we could even put one together like this. Suppose we said we're selling within the last 7 days before the flight is our highest price, then days 8 to 14 is the middle price, and then after 15 and more is the lower price. If the customers know we do this, they might start hopping from class to class. Like a business traveler might say, oh, if we book 8 days in advance, we get a discount. So let's try to plan our business trips 8 days in advance because we know how the airlines work.
Right.
So if you kind of have too many of them, you might find that those lambdas change. So for example, let's say lambda 2 would be 40 people normally show up within the last 7 days. Well, if you give a price 8 days to go, that's a lot lower. They might look for it, and then this would become like 35, not 40, because some of them are looking for the other class. So there's kind of a correlation between the lambdas.
Correct.
If you add, so yeah, so so what we might do is we might say, because the truth of the matter is, as that people running the airlines, we can have as many classes as we want. So we might say, let's add a new class. Well, that might change the parameter that we use. It might make it a little lower because people will hop from class to class. Not all of them. Some people don't know they're traveling till the day before. But some people do know around 6 or 7 days, and if they know that planning 8 days in advance gives them a better price, they might use it. So they'll be somewhat correlated. But what's kind of good about Matlab, it accomplishes a lot with a few lines of code. And it runs the experiments pretty quickly. So, okay.